As you can see from the title of this video, we are going to be talking about two new triangle congruence theorems. This time it's ASA and AAS. Now some people might think, how are these two different? They both involved two A's and an S, but remember, the order in which those letters appear is significant. It's symbolic of, I guess we could say it's symbolic of the difference between them, and we'll get into that in a few minutes. But first I have a question that I want to think about. It says, is it possible for the two triangles at the right over here to not be congruent? And explain why or why not. And so if we look at these two triangles, remember, if they were not congruent, that means that at least one of their 6 measurements, meaning the 3 angle measures and the 3 side lengths, one of those 6 measurements has to be different, because if they're all 6 the same, then those triangles are identical, they're congruent, they have the same size and shape, remember. So I'd look at this and I'd ask myself, is it possible that one of the 6 measurements on this triangle over here on the right, or on the left, I'm sorry, is different than one of the 6 measurements over here that it should match up to? And we'll notice that 4 of those measurements are the same, right? A side of 3 centimeters, a side of 3 centimeters. So we know that that side and that side are congruent. We have a side of 5 centimeters and a side of 5 centimeters. So we know that those two sides are congruent. We have a 65-degree angle here and a 65-degree angle there. So those angles are congruent. And we have a 45-degree angle here and a 45-degree angle here. So 4 of the 6 measurements are the same. So that leaves only 2 possibilities for ones that could be different. Either this angle and this angle have to be different, or this side and this side have to be different. Well, let's think about these 2 angles here. Let's call this one up here, let's call it x degrees for now. Let's say this is x degrees. Let's figure out what that would be, because we know these 2 angles are 65 and 45, and we know that all 3 of them have to add up to 180. So x plus 65 plus 45 has to equal 180. So x plus 110 has to equal 180. So that means x would be 70 degrees. And then over here, I have a 45-degree angle, a 65-degree angle, and then a missing angle. So that one also has to be 70. So this is 70 degrees, and that's 70 degrees. So that only leaves this one as this side length as a possibility for what could be different between the 2 triangles, because now we see that 5 of the 6 measurements we know are the same. So we'd maybe think, well, can this side length be different than this side length? But if we stop and think for a second now, we have a side here that's congruent to a side here, and a side here congruent to this side. And now we have the angle that's between them congruent. The 70-degree angle is included between these 2 sides, and this 70-degree angle is included between these 2 sides. And that means that these triangles now have to be congruent by SAS. So can they be not congruent? We would say, no, they must be congruent because of SAS. And I might put in there the missing angle on each triangle must be 70 degrees, just to kind of explain why initially we didn't have those angle measures, but we kind of figured it out. So those 2 triangles must be congruent. Now next I have another kind of a thought experiment. Suppose you and a friend are both asked to draw triangle ABC with the measure of angle A equaling 30 degrees, angle B being 45 degrees, and the distance from A to B being 3 centimeters. Is it possible for the 2 of you to draw 2 triangles that are not congruent? And explain. Well, let's just kind of draw this out, right? We would have one side, AB, that's 3 centimeters. So we'll just kind of say, all right, there is going to be segment AB, and it's going to be 3 centimeters. And then our friend draws their own segment AB. You know what? I'll change the color there. I'll do that one in this color. So our friend draws their own segment AB that is also 3 centimeters. We put angle A as a 30-degree angle over here, so we put a 30-degree angle over here. It doesn't say how long this side's going to be, so I'll just kind of show that this is a ray that could theoretically kind of keep going in that direction. But it's 30 degrees. And our friend does the same thing over here. All right, they make a ray that's 30 degrees, and it could keep going out that way. And then angle B, it says, is going to be 45 degrees, so that's about half of a 90-degree angle. We can kind of eyeball that being about right there. So this is going to go out that way at a 45-degree angle, and then our friend's going to do something similar, so about halfway between a 90-degree angle. So it's going to kind of go out that way. So now the question is, could these two triangles not be identical? Well, first of all, again, if we think about these, the 6 measurements of a triangle, is there any possible way that one of the 6 measurements on this triangle will be different than one of the 6 measurements on this one? We can see we've already determined 3 of them that are the same, but actually the 4th angle would the 4th measurement, which would be the 3rd angle, would have to be the same for the same reason we talked about up here, that if these 2 angles are the same as these 2 angles, then that 3rd angle will be the same. So now the question is, could these sides here and here be different than these sides here and here? But we'll notice that the 3rd side, or the 3rd corner, C, there's only really one place that it can be on each triangle, right? C has to be right here for this triangle, and it's going to be right here for this triangle. And those two spots are basically, we don't have a choice about where that's going to be. It's been determined for us by the fact that this is a 30-degree angle and this is a 45-degree angle. And so these 2 rays, they only have one place that they could intersect. And so what that means is that these 2 sides here and here are going to be congruent, and these 2 sides here and here are going to be congruent as well. So that means that all 6 measurements are going to end up being the same. Now, I don't know exactly how long segment BC is going to be on each triangle, or exactly how long segment AC will be on each triangle, but I know they'll be the same. So to answer my question, I'm going to say, is it possible for the 2 triangles to not be congruent? No. The location of C will be the same for each triangle, because there is only one intersection between, I'll say, the 2 rays forming the 30-degree and 45-degree angles in each triangle. So essentially what I'm trying to say there is that that point C and that point C has been determined for us by the fact that we used a 30-degree angle, a 45-degree angle, a 30-degree angle, and a 45-degree angle, and that the vertices of those angles are each 3 centimeters apart. Right? So there's no way that we could make 2 different looking triangles there. So those 2 ideas are kind of what we're going to get to here. You'll notice that in this picture, when we first started, we had 2 side lengths and we had 2 angles, but neither of the angles was the included angle between the 2 side lengths. Here we had 2 angles in one side length, and in both situations, with the given information that we had, the triangles ended up being congruent no matter what, like they had to be congruent. And that's going to kind of lead us into the 2 theorems that we're going to learn about in this section. Theorem 4-6 is called the angle-side angle, or ASA triangle congruence theorem. We have a picture here that kind of illustrates it. If these 2 triangles are marked in this way, that they have these parts congruent, you'll notice that they have an angle congruent to an angle right here. We have another angle congruent to an angle over here. And then we have the segment that's between those angles, the segment that kind of connects the vertices of those 2 angles, is congruent. In that case, we would be able to say that triangle MNL must be congruent to triangle. Now I got to think about the order that I'm going to put these vertices in. What matches up with M over here is S. What matches with N in the other triangle is T. And then what matches with L would be R. So these 2 triangles would be congruent. In words, this theorem says, if 2 angles of one triangle in what we call the included side, so 2 angles in the included side, and I'll define that included side in just a second. If 2 angles in the included side are congruent to 2 angles and the included side of another triangle, then the triangles are congruent. And when I mean included side, when I say included side, what I mean is the side that connects the vertices of the two angles. Or you can also think of it's the side that's between the two angles. And that's why we say ASA, and that S for the side is located between the A's that represent the angles. The side is between the angles, just like what we see in this picture here. So that is what we call the angle side angle theorem. Then the other one is called angle side, and let's kind of work down let's talk about this one real quick. You'll notice that again what we have in these two triangles are two pairs of angles that are congruent and then a side that's congruent, but this time the side is not located between the angles. It's what we call a non-included side. And so let's start with the writing part over here first. If two angles and a non-included side of one triangle are congruent to two angles and a non-included side of another triangle, then the triangles are congruent. Okay, so non-included this time, so it won't be the side that connects the vertices of the angles or the side that's between the angles. It's one of the other ones. And typically what we're looking for is it to be like the same side on each triangle. So you'll notice that the side that's marked here is across from the angle that has one arch on it. And then the same thing is happening over here. The side that's marked is across from the angle that has one arc on it. So it's kind of the corresponding, I guess is what we would use, the corresponding side of each triangle is congruent. And that's called AAS, right? So when we see that in that picture there, we know that triangle UVW would be congruent to triangle. So U would go with X, V matches with Y, and W matches with Z, right? And the reason why we know this would be true is because, well, if ASA works, then AAS will also work, just for the idea that if these two angles are congruent to these two angles, then by what we call the third angle theorem, it would guarantee that angle W and angle Z would also be congruent. And in that case, then we would end up with ASA, two angles that are congruent here and here, congruent to these guys over here, and then now the side that's between them, or the included side, is congruent. So AAS is just kind of like a shortcut so that we don't have to, if we were looking at a picture like what we had here initially, where this was what was marked, we wouldn't have to go through some kind of explanation that would say, well, if these two angles are congruent, then these two angles are congruent, and then we'd have ASA. We can just kind of shortcut it right to saying, well, AAS makes these two triangles congruent because these two angles and this non-included side are congruent to these two angles and this non-included side. And by using AAS, we're kind of implying that the third pair of angles would be congruent, and then ASA would be present in our diagram. Okay, so now that takes us up to 4 different triangle congruence theorems. We had SAS and SSS, and remember, order matters, so this one, SAS, places the angle between the two sides, what we call the included angle. And then today we added ASA, 2 pairs of angles congruent and an included side. And then because that works, it means that AAS also works, where 2 of the angles are congruent, but then a side that's not in between them is congruent between the triangles.